Okay, good afternoon. Class has grown. Is it Parents' Weekend or something? Oh, it is? Welcome, parents. I hope you enjoy this. Last lecture, we were looking at the minimum cut problem. And we sort of went deeper into the contraction algorithm. Which is this sort of randomized process that has a success probability of this sort of large product, which telescopes out to be 1 over n choose 2, or approximately 1 over n squared, but takes linear or quadratic time to m or n squared time to run. So we developed this recursive version which had a runtime of roughly n squared and a success probability of 1 over log n or so, right? So that's what we spent most of last lecture on. This is a Monte Carlo algorithm, so high probability of success, but we don't know if our answer is correct or not. I will also mention that it found all of the min cuts with high probability, and along the way also proved that the maximum possible number of min cuts is n choose 2, which is tight for the cycle. So that's what we got out of the contraction algorithm. But then I introduced you to this completely other approach to solving the minimum cut problem, which is due to Gabo. It is really the sort of natural analog to augmenting paths for max flow. Right? We take that notion of a duality between the maximum number of paths that you can pack into a graph and the minimum cut that separates the vertices S and T. And we apply that to the minimum cut problem by thinking about augmenting trees for the global min cut. Right? And the sort of natural augmenting paths algorithm, which most of you have seen before, takes order m time per path, which means that it takes you order mv time to find a max flow of value v. And of course, when you find that max flow, when you get stuck, that reveals the minimum ST cut in that graph, is the reason that you can't find another path. And in a similar vein, Gabo gave an algorithm that would add one tree to the graph in roughly linear time, and that yielded an algorithm for finding a max tree packing which in the same way also reveals the minimum cut of the graph. Okay, and I sketched this out. I'm not going to show you the augmenting tree algorithm because it's quite sophisticated. It relies on this interesting matroid intersection algorithm. You're not actually augmenting by trees. You're augmenting by a set of edges that increases the degree of the directed degree of every vertex in the packing by 1. But it's very sophisticated, but we can just use it as a black box the same way as we can use an augmenting path algorithm as a black box. So then the reason that I introduced you to Gabo's algorithm is to continue exploring this idea of sampling, right? The sort of core idea of sampling is that if your expectation is some quantity mu, epsilon delta, then the probability that you are within epsilon of it, or sorry, the probability that you are not within epsilon of it. Where'd my erasers go? Okay. Oh, there they are. Probability that you're not within epsilon of your mean is at most e to the minus epsilon squared mean over 3. This is for epsilon less than or equal to 1, which is the case that we're going to be interested in. This is just the usual Chernoff bound, right? And so this is sort of this core principle of sampling, is that if you expect something, then if the expectation is large enough, you'll be close to that expectation with high probability. And we're going to apply that idea to this idea of G of P, where we sample every edge of the graph with probability P. And so if we do that, then the expected number of sampled min-cut edges is what? Give the parents a chance to answer first. No? Okay, students? Yeah? Exactly, which I define to be C over there, right? So that's the expected number. I'm not going to say it's the expected min-cut, right? Because we're generating this other graph, which may have a min-cut somewhere else. But it is the expected number of edges that we sample from this cut. And therefore, as long as PC is large enough, right? Then we can say that the number of sampled edges is within 1 plus epsilon of this target with high probability. And here I'm taking delta to be, 1 over a polynomial in order to get my high probability bound, right? So this was promising. It sort of said that if we looked at the sampled min-cut, it would give us a value which is very close to its expectation of PC. And so we could then, we know P, so if we take that value and divide by P, we'll get a value that's very close to C. And so we'll reconstruct the minimum cut, right? Now the problem with that approach is that although we can find we've been talking about minimum cut algorithms, we can look for a minimum cut in the sampled graph, but that may be a different cut, right? As we sample some other cut of G, which has more edges than the minimum cut, we may sample fewer edges from it than we sample from the minimum cut. And so that cut becomes the minimum cut of the sample. That's the cut we find. And what if we use that as our estimate for the minimum cut value instead of the sample from the graph? But I sketched out last time how this is okay, right? Maybe, right, take this idea, maybe every cut is within 1 plus or minus epsilon of its expectation, right? So that would mean that a cut of some value, say V, is within 1 plus or minus epsilon PV in the sample, right? So why is that good? Can somebody sort of sketch out, if this happened, if every cut in the sampled graph is within epsilon of its expectation, I claim that I can reconstruct the value, I can estimate the value of the minimum cut from the sample. Yeah? Exactly, right? The original min cut has value at most 1 plus epsilon times PC, right? So that means that the min cut of G of P is less than this, because there is at least one cut that has this value, right? So what cut could become the minimum cut in this sample, right? Well, if we start with a cut of some value v, our argument is that its value is going to be more than 1 minus epsilon PV in the sample, right? So to be the min cut of G of P, we would need for its value, which is at least 1 minus epsilon PV, to be less than the value of, or less than or equal to, the value of the minimum cut in G, in the minimum cut in the sample, right? But now we cancel out the p's, and we find out that the value of that cut, the starting value of that cut, is within 1 plus epsilon over 1 minus epsilon of the minimum cut value, right? And for small epsilon, 1 minus epsilon is about 1 plus epsilon, and 1 plus epsilon squared is about 1 plus 2 epsilon, so I'll just say this is about 1 plus 2 epsilon times c. So in summary, if every cut is within epsilon of its expectation, then the min cut in G of P is a less than 1 plus 2 epsilon times minimum cut in G. And so we have found an approximately minimum cut in this sampled graph, right? And the nice thing is that, like, Gabo's algorithm runs very fast in the sampled graph, right? The number of edges scales by our sampling probability p. And similarly, we've just argued that the minimum cut is at most 1 plus, or I'll just say order of PC, right? So you put these together, and you find out that Gabo's algorithm has a runtime of p squared times MC in the sample. So we've sped up by a p squared factor. Sorry, a question? No? Okay. So that's where we left off last time. And I said, you know, it'd be really nice if every cut is within 1 plus or minus epsilon of its expectation. But why in the world should we expect that to be true? Right? We have this Chernoff bound that says that a particular cut is close to its expectation with high probability. Again, this is if I'm choosing delta to be log n or so, or delta to be 1 over n or so. So mu is going to be like, right? So the mu that we're going to be working with is going to be about 1 over epsilon squared log n. Right? I'm assuming you're all used to this now. Right? So at that value, we can say that any particular cut is close to its expectation with high probability. Now, I said here about the minimum cut, but every other cut is bigger. So every other cut has a larger expectation. So also each other cut is close to its expectation with high probability. But that's not enough. How come? Yes? Right. So we know that each cut is within its expectation with high probability, but that just means a 1 over polynomial chance of failure, right? In other words, the probability that something goes wrong with a particular cut is less than 1 over n to the 4th or whatever other number I want, right? The problem is that the number of cuts is equal to, if I want to be really precise about it, 2 to the n minus 1 minus 1, right? I have to assign a left side or a right side to each vertex. So that's 2 to the n ways, but I can swap left and right if I want to, right? So that gives me 2 to the n minus 1, and why am I subtracting 1? What was that? Yeah, I'm not allowed to put everything on one side, right? So that leaves off one. But it's basically 2 to the n. And so, although this is a small probability for many purposes, it's much too large a probability if we're just going to use the union bound. Except, this is what I ended last lecture with, it turns out that the union bound works anyway. Okay? So the theorem we're going to prove if you generate g of p such that pc equals order log n over epsilon squared, then with high probability, every cut is within 1 plus or minus epsilon of its expectation. Okay. And so, yes, question? Okay. So the way to think about it is that each cut, right, you're specifying for each vertex, does it go left or right? Yes? And that, there are 2 to the n different, there's n vertices, so you're making you're making 2 choices n times. So that's 2 to the n ways of splitting the vertices into 2 groups, right? However, you have to exclude, you're making the same cut 2 different ways, right? Because you might put some stuff on the right and some stuff on the left, or you might flip it and put the left stuff on the right and the right stuff on the left. So that means you have to you have to divide by 2 the counting that you do. Or another way to look at it is to say, I'm going to fix vertex 1 as being on the left side. And now I'm going to assign a left or a right side to the other n minus 1 vertices. Okay, so that gives me the 2 to the n minus 1. But this includes one forbidden partition, which is the partition that puts everything on the left side. So that's why you subtract 1. Okay. All right, so if this theorem is true, then all of my wishful thinking up there works out, right? If this theorem is true, then this simple algorithm, simple because we're not actually explaining Gabo's algorithm, right? But this simple wrapper for Gabo's algorithm gives us an approximation with a running time of order p squared mc. And actually, let's plug in, right? This is saying we should use our usual mu epsilon delta. So what's that going to give us for a runtime here, right? If pc is 1 over epsilon squared with some logs, that means that p is 1 over epsilon squared c, right? So I plug that in over here, 1 over epsilon squared c. I have 1 over epsilon to the 4th c squared times mc, which is m over epsilon cubed c. Okay. So this runtime looks a little bit weird because it's actually getting faster the bigger your minimum cut is, right? On the other hand, we know that there's a relationship between m and c, right? In order to make the minimum cut large, you're going to have to make m large as well, right? We argued that m was bigger than nc over 2, right? So what you're actually getting here is a term that's like n over epsilon cubed. And of course, you also have the linear cost of constructing the sample and so forth. Okay? But essentially, this approximation algorithm is linear time. Yes? Correct. So this is an issue that we will have to deal with, right? This is saying, if you set P appropriately, good things happen, but how do you know how to set P appropriately if the whole goal is to determine C, right? So let me come back to that after we've proven our main theorem. Yes? Sorry. That's why I put a tilde here, right? So there's a few logs that are going to get thrown around that are going to mess up they're going to make the notation messy, so I'm just hiding them inside of that tilde notation. And I promise you it's never more than 3 or 4 logs, so we're not doing crazy things with 50 log powers. Okay, I have done algorithms like that, but we're not going to do them today. All right, so we have to prove this theorem. And what could give us this much stronger result than we could expect naively, right? So I said that, we set this bound, we set this P so that PC is log n over epsilon squared. This is our mu epsilon delta, our usual mu epsilon delta here, right? I've set it so that the min cuts get sampled with probability to have expectation mu epsilon delta, and so there's a high probability that each min cut is close to its expectation. But there's exponentially many cuts. Why? What could give us hope here? Yes, Richard? Okay, so one path for hope might be to exploit dependence, right? Cuts overlap, right? And so they actually, the fact that one of them is close to its expectation might tell you that the other one is also close to its expectation, right? I don't know how to use that leverage, partly because it's bidirectional, right? It can't be too small and it can't be too large. And so if I'm telling you this cut is not too small, maybe that makes the next cut too large. There's also a weird fact, which is that minimum cuts, I won't go there. So I don't know how to use that idea. So let's look for a different one. Yes?
The other cuts are larger than their value.
Good. So we proved last time that there are only n squared min cuts, right? So the theorem does hold for the min cuts, right? Because we have this high probability result. We have to worry about the other cuts, but they're not min cuts. They're bigger. And if they're bigger, what does that do to our Chernoff bound? Yeah? Exactly, right? If I look at cuts that are twice as big as the minimum cut, then their expectation is twice as large, right? Which means that if we pull off our Chernoff bound, right, e to the minus epsilon squared p times the particular cut value, right? So if I look at cuts that are twice as large, I'm actually squaring this bound. It goes down exponentially with the size of the cut. Okay? And so if there aren't too many small cuts, right, maybe we're in good shape. Maybe there's not too many small cuts, so the Chernoff bound being loose is okay there. And yeah, there are tons and tons of cuts, but if most of them are really big, then they'll get a very small probability of deviation. And so the union bound will work. Okay? So hopefully that motivates asking this question about, how many small cuts are there? Okay? So for that, I'm going to give you a lemma. Right? About the number of what I'm going to call alpha minimum cuts. Okay? And I won't spoil the fun by telling you what the answer is. Let's derive it and then plug it into the lemma. So if we're interested in showing that there aren't a lot of small cuts, what machinery might we hope to use? Well, how did we prove that there weren't a lot of min cuts? I'm getting used to certain hands. Is there anybody else remember anything? Yeah? Exactly. The way we bounded the number of min cuts was we said the contraction algorithm has at least a 1 in n squared chance of finding a particular min cut, but it only finds one, right? Or to put it another way, right? Each min cut has to have a 1 over n squared chance of being found. But those probabilities can only add up to 1. So there can only be n squared of those min cuts. So we're going to use exactly the same argument, right? Let's consider an alpha minimum cut and ask about the probability that the contraction algorithm finds it. Okay. Yes, Val? So that is a cut whose value is alpha times, it's literally, it's as the English sounds, it's alpha times the minimum value of the cut. What was that? Oh, I see. Yes, you're right. So the definition here is a cut of value alpha times the minimum. Okay. And I'm going to include, I'm actually going to be a little bit sloppy about talking about alpha minimum as exact. This cut is, when I say this cut is alpha minimum, I probably mean that its value is exactly alpha c, but when I talk about sets of alpha minimum cuts, I may include the ones that are smaller. It will hopefully make sense in context. So, how do I analyze the probability that the contraction algorithm finds a particular cut of value alpha c? I basically have the formula on the board already, right? What do I have to change? Right? So over here, I wrote a formula that we telescoped for the success probability of the contraction, and the probability that it finds a particular minimum cut, right? How should this formula be changed if instead of talking about a minimum cut, I'm talking about an alpha times minimum cut? Yeah? Exactly. Mincut had C edges, and I said the graph has NC over 2 edges, at minimum if the minimum cut is C. Now the graph has, now I'm looking at a cut of alpha C edges, so it just multiplies the probability of choosing one of those edges by a factor of alpha. So my new formula is 1 minus 2 alpha over n times 1 minus 2 alpha over n minus 1, and so forth. 2 alpha. I'm going to write out a few more terms so that we can see what happens. All the way down. Now, we have to be a little bit careful because at the end, if I say something, right, if we ran the contraction algorithm all the way, my final term would be 1 minus 2 alpha over 3. What's wrong with that? Yeah? Sorry, go ahead. Yeah, if alpha is large, this could be negative. So we have to have some sort of early stop at something like 2 alpha plus 1 vertices. Yes? So we have to make the algorithm a little bit more complicated. We're going to do these random contractions until we have 2 alpha plus 1 vertices, right? Now we're trying to pick a random cut, but we can't do contractions anymore. So what should we do instead? Well, let's just pick an arbitrary random cut, right? Random partition, right? So if I have 2 alpha plus 1 vertices and I take a random partition, what's the probability I output the cut I'm looking for? Yeah?
1 over the number of remaining nodes minus 1.
Exactly, and I just said that the number of remaining nodes is 2 alpha plus 1, so it's about 1 over 2 to the 2 alpha, right? So we'll have that extra term. But the important stuff is what's happening before. What can we say about the probability that the alpha minimum cut survives all of the contractions? Well, one particularly easy case is where alpha is a half integer. Okay. Because then 2 alpha becomes an integer. So I'll have something like, let's say 1 minus 5 over n, 1 minus 5 over n minus 1, 1 minus, actually I shouldn't have used 5, it's too big. Let's just look at 3. 1 minus 3 over n minus 2, 1 minus 3 over n minus 3. What's nice about this product? Yeah? It's still telescopes, right? Now we have n minus 3 over n times n minus 4 over n minus 1 times n minus 5 times n minus 2 times n minus 6. Oh, here's the n minus 3 that is going to cancel this n minus 3, and all of the later terms are going to cancel. So what we're left with now is, in the 3 case, over here we have 1 over n times n minus 1 times n minus 2, right? And at the other end, where we finish, we're going to have 3 times 2 times 1, right? So what we actually have is n factorial over n minus 3 factorial in the first part, and then 3 factorial here, all inverse, which is just n choose 3 inverse. But then we have to then we multiply it by this little factor at the end. Okay. But of course, this n choose 3 inverse is about n to the minus 3, and here I have 1 over 2 to the 3. So this is basically 2n to the minus 3 if I'm looking at alpha equals 3 halves. Yes? Everybody happy with that? Okay, and now you can see that this generalizes, right? So for any half integer alpha, the number of min cuts, or the number of cuts, a value at most alpha c is at most 2n to the minus 2 alpha. So any questions about this proof for half integers? No? All right. Now, this is actually tight enough this is actually enough to prove the theorem. You can actually, you can generalize it to non-half integers. If you want to talk about non-half integers, then you just need to use what are called generalized binomial coefficients. Which are binomial coefficients where the second number is not an integer, right? So you can talk about something like n choose 2.7, right? And n choose 2.7 will be the number of cuts whose value is less than 1.35 times the minimum, right? And the point is that even for fractional values, for non-integer 2 alpha, n choose 2 alpha is order of n to the 2 alpha power. Okay? It uses, you can define it in terms of what's called the gamma function if you're familiar with the gamma function, right? The gamma function is the extension of factorials to non-integers. And so you just throw in these factorials. You just throw in the gamma function where the binomial coefficients use factorials. Okay? So you can trust me on this, or you can just think about applying the half-integer only version of this lemma in order to prove the theorem that I'm going to prove. So now that we have this lemma, we can go back and prove the theorem, right? That's not it. Right, so now we are going to do the theorem as a union bound. So first of all, let's consider the min cuts, right? There's only n squared of them. Each is sort of diverges by more than epsilon with probability, say, 1 over n to the 4, if I choose my constants properly in my P, right? So the probability that any diverges is less than 1 over n squared. Okay. So let's think about the other cuts. And what we're going to do is we're going to write them in increasing order. C1, C2, C3, and so on up to C sub 2 to the n minus 1, the biggest cut. Okay? I claim that we just proved that there are only n to the 2 alpha. I'm going to leave off the O's so that the board doesn't get cluttered. So remember there are some constant factors here that don't matter. Cuts of value less than or equal to alpha c, right? So if I turn that around in this ordering, what this tells me is that the kth cut value is at least alpha times c. Right? When k equals n to the 2 alpha. Right? I'm just counting the small cuts. So I plug that in. C sub n to the 2 alpha is bigger than alpha c. Okay? But now, if I flip this around, I take some logs of both sides, I find out that alpha in this formula is equal to the log base n squared of k. Yes? So if I plug that in over here, I can say that c sub k is bigger than log base n squared of k times c. Right? So, what can I say about the probability of an epsilon deviation for this cut? Well, if this is the value of the cut in the original graph, what is its expected value? Yeah?
P times the log base n squared of k times c.
Exactly. The expected value of this cut is P times ck, which means that the probability of deviation by epsilon can be Chernoff bounded. Right? Sorry, ck. Yes? So now I just plug in the value that I found for ck, right? E to the minus epsilon squared p times log base n squared of k times c over 3, right? But now I can sort of pull down the log factor, right? Sorry, I got ahead of my notes. This is, but sorry, the epsilon here, remember how we set the epsilon here to, hold on a second. PCK. Right, let me change the notation a little bit. So this is correct. This is e to the minus epsilon squared times alpha k, which is that multiplication. And then we're left with pc divided by 3, right? ck is alpha k times c, right? But remember, we set this pc to be equal to our mu, our magic number mu, right? So this is e to the minus epsilon squared alpha k times mu divided by 3, right? But remember that we set mu so that e to the minus epsilon squared mu over 3 was like 1 over a polynomial, right? So this is just equal to, let's say, n to the minus 4 raised to the alpha k power. Yes? I'm going to keep going unless somebody stops me, so stop me if it doesn't make sense, right? So, but we just said that alpha k is log base n squared of k. So this is n to the minus 4 times log base n squared of k, and that is, right, you've got this 1 over log n squared here and an n to the minus 4 here, so this is just equal to k to the minus 2. Okay, because n to the minus 4 over log of n squared, right? Here we have a 2 log n, so it's n to the minus 2 over log n. N to the minus 1 over log n is e, so this is just e to the minus 2. Okay, and then you raise that to the kth power, to the log k power. Everybody happy? All right. So now the probability that any cut deviates can be union bounded, right? Is at most the sum over all k's of e to the minus epsilon squared pck over 3, right? But we just said that that's just equal to the sum over k of e to the minus of k to the minus 2, right? But we only need to look at, like, we already bounded the first n squared cuts because they were, like, we said there are n squared minimum cuts, and the regular high probability result is enough to take care of those first n squared cuts. So we only need to look at sort of k bigger than n squared, right? And so now we just have this geometric sum, right, that whose first term is n to the minus 4, right? So this is just going to be order of n to the minus 4. So, yes? Or sorry, it's n to the minus 3, right? We use our usual integral trick, right? Integral from n squared to infinity of k to the minus 2, right? Gives us k to the minus 3, k to the minus 1 from n squared to infinity, which will give us n to the minus 2. Yes? And again, the reason I'm being sloppy with these constants is that we can make these constants whatever we want by changing the constant in our mu term. Right? If you right, so the whole point of choosing mu to be log n over epsilon squared is that the constant that you put in front of your mu is what determines the exponent in your high probability result. And that all floats through here. So if we increase the constant in our mu, then we can drive this exponent down. We can make it as large as we want. Yes? Well, we know they're not smaller than min cuts, right? And if they're bigger, it only helps us. Okay? So the point is that we use C as the bound for the first n squared cuts, and after that, we use this alpha k term as the bound. Okay? Any questions? So now we're done, right? We have now proven that even though there are exponentially many cuts, when you sample with high probability, every one of them will be within epsilon of its expectation. And therefore, we will be able to use this very simple sampling procedure to estimate the value of the minimum cut. Any questions? Yes? Good. So, we had lingering this question, or this issue, which is that P depends on C. Right? We're choosing P to be 1 over C times some logs and 1 over epsilon squared, which it appears we can't do until we know C. So how do we address that problem? Yes? Yeah. We guess, right? So what I can say is I wouldn't actually do it by binary search. I would do it by repeated doubling or repeated halving, and you can kind of think of it in either direction. Okay? So one idea would be to start with a very, and this is actually probably the better idea, start with a very conservative estimate for C. Let me say maybe C is 1. Okay, if C is 1, well, if C is 1, I actually can't sample. The variance will be too large. Right? But I can check if C is 1, right? How do I check if C is 1? Using the machinery that we've developed. Well, I just use Gabo's augmenting tree algorithm, right? I try to pack a tree into the graph, right? And if I then can't pack it, if I'm then stuck on packing my second tree, I know that C is 1. In fact, I can do this as long as C is less than mu, right? If C is too small for me to sample, then I can directly use Gabo's algorithm. Okay? So I will use Gabo's algorithm to pack up to mu trees. Okay? And if I fail to pack mu trees, then I have found the minimum cut and I'm done. If I succeed, or 2 mu. If I succeed in packing 2 mu trees, this tells me that the minimum cut is at least 2 mu, so it is safe for me to sample with probability half. Right? And to try doing my packing in that sample. And, if in that sample I still can pack too many trees, it means I'm still underestimating the cut, so I'll try doubling my estimate again. Right? And each time I will have an estimate for the cut, I will sample based on that estimate, I will pack until the packing shows me that I have too many trees, right? More than 1 plus epsilon, mu epsilon, delta trees, right? And at that point, I will stop and say, no, my probability was too large. I will cut the sampling probability in half and try again. And I keep doing that until I sample at a low enough rate that I run out of trees. And that demonstrates for me that I have found the appropriate C. Okay? Now, you might feel a little bit nervous about this, and I think that's connected to the fact that this algorithm is, again, a Monte Carlo algorithm, right? Why is this a Monte Carlo algorithm that we've just described? Yeah?
We don't know that we found the main cut by confidently.
Yeah, right. We take this sample, we pack trees in it, and we find a min cut in the sample. But you could have very bad luck, right? It could be that the sample takes no edges from this really gigantic cut. And so that appears to be the minimum cut, and that's the one we return. But we're just wrong, right? Nothing in this procedure certifies that the cut we found is the actual minimum cut. So that is something that I'll address after the break. So take 2 minutes, get up and stretch, say hi to your parents, and then we will resume with figuring out how to make this algorithm Las Vegas. All right, let's resume. We have now this Monte Carlo algorithm. The natural question is, can we make it Las Vegas? Can we somehow be confident in the value of our approximation? Or not just the value, but actually, we found this cut that we think is close to a minimum cut, right? Its value is at most 1 plus epsilon times the minimum. But how do we know? Okay. What tools do we have at our disposal that can certify the value of the minimum cut? Yeah? Yeah, so in Maxwell min-cut, there's this really wonderful duality theory, right, that says that how do you know that this is an ST min-cut? Well, you know because you can find this packing of paths whose value is equal to the value of the minimum cut, of the ST min-cut, right? Or, and it will actually saturate the ST min-cut, right? And as we discussed, Gabo gives us this really nice analog for global min-cuts, which is that instead of packing paths, you pack trees, right? So if the min-cut is C, you can pack C trees into the graph. Okay. So that's nice, but it doesn't seem to help us directly because if we are going to certify our approximate minimum cut by packing C trees, well, packing C trees is going to give us the actual minimum cut, right? We don't need to settle for an approximation at that point. And the downside is that packing C trees takes a lot of time, right? So we might hope to certify with a tree packing. But that's too slow. Okay. But now let's remember that we are only trying to certify that our cut is approximately minimum. So do we need a perfectly maximum tree packing in order to certify that our cut is approximately minimum? What would be enough? Yeah? Exactly. Certify with some sort of 1 minus epsilon times optimum. Or let's just say C. Right? If I find a cut of value less than 1 plus epsilon C, and I find a packing of value greater than 1 minus epsilon C, right, then the actual min cut is going to be somewhere in between them, right, which will tell me actually two things. It will tell me, right, these certify each other, right? The small cut tells me that my packing is approximately maximum, and the large packing tells me that my cut is approximately minimum. Yes? And you probably see this already, but if I'm actually looking for an epsilon approximation, what I'll do is I'll just aim for epsilon over 2 cut and epsilon over 2 packing, and now the ratio between them will be at most 1 plus epsilon, and so I'll be with it, right? So I just need another factor of 2 in my approximation to be able to certify these things with each other. Everybody accepts that? Okay, so this is hopeful. We don't need an exact, perfect maximum tree packing. Okay? But it doesn't give us a path forward right away, because packing 1 minus epsilon times C trees is only going to save us the 1 minus epsilon factor in Gabo's algorithm. So what can we do? Yes? Very good idea, which I'll come to after we get that approximate packing. Okay? But first we have to get that approximate packing. Okay? So I claim that in a sense we have an approximate packing because we took this sample, right, with probability p, right? We generated g of p. And we said, the min cut of p is about pc. And so we're going to find the minimum cut by tree packing, right? And so we have this graph with a min cut of value pc. And we pack trees in it, which means we find about pc trees in that graph, right? But there's these epsilons, right? So we're going to find maybe 1 minus epsilon times pc trees, right? But the min cut is only pc. So we've actually found a approximately maximum packing relative to the cut of that sampled graph, right? So the insight is, let's do this for lots of copies of the sample, okay? So imagine that we partition G into 1 over P subgraphs. Partition the edges of. So we're not making a cut of G. We're dividing the edges up into 1 over P groups of edges randomly. Okay? What can I say about each group? Each of these graphs looks like G of P, right? Because each edge lands in that graph with probability P. So what can I say about this graph? Well, I can say all of the things that I just proved, right? I can say that the min cut is at least 1 minus epsilon times its expectation. Yes, Balak? Yes. Good. So what I said is true and what you said is also true, right? Each of these GIs is a uniform random sample of the edges of G. Now what you said is that these GIs are dependent on each other.
No, what I said is that in one specific GI, you know the total sum of edges, like the total number of edges in it. So if you know that one edge is sampled, then another edge is just like sampled. Right?
No, that's not how I'm doing the partition. I didn't say here that you should partition into equal numbers of edges, right? I'm just making 1 over P graphs and sending each edge to one of the graphs at random. Okay? So each graph really does look like a uniform random sample from the edges. Okay? So our sampling theorem, which tells us that all cuts are close to their expectation, tells us that no cut is going to be less than 1 minus epsilon times the min cut. Right? That tells us that GI has a tree packing of 1 minus epsilon PC trees. Yes? So if I combine them all, if I combine these 1 over P copies, or these 1 over P subgraphs, or these 1 over P packings, I end up with 1 over P times 1 minus epsilon PC, which is to say 1 minus epsilon times C trees. Yes? But remember, I partitioned the edges. So each graph is making trees out of a different set of edges. Right? So they're disjoint. So they can all be combined. Right? So this simple algorithm, just divide up the edges and run Gabo's algorithm in each subgraph, gives us our approximate tree packing. Why is it better? Well, what's the runtime of this algorithm? Well, I'm running in 1 over p subgraphs. What's the runtime in each subgraph? We already worked this out, right? Because each subgraph is just a sample. So I'm just asking what's the runtime of the algorithm in G of p? Oh, some of you are very quiet today, making me look bad in front of your parents. Right, is this quantity we worked out right here? Sorry, where did I put it? Here. Right? This is the runtime for one sample. Right? So the runtime is 1 over p times roughly p squared mc, but now you can see where we win. Right? We have to do this 1 over p times, but we sped up by a factor of p squared, so it's order pmc. What was my p? It was log n over epsilon squared c. Right? So this is right. So the p cancels the c, and we have m over epsilon squared. So my tree packing algorithm is also linear time, independent of c. Right? It has a dependence on epsilon, of course, but it's independent of c. Right? And so this duality is quite wonderful for us, right? We have these two algorithms that are both Monte Carlo, right? The tree packing algorithm is Monte Carlo. I might have bad luck and fail to find a lot of trees. The cut approximation algorithm is also Monte Carlo. I might have bad luck and find a really large cut, right? But if I run both of them, right, then they certify each other, and I end up with a Las Vegas algorithm. The tree packing algorithm is the slower of the two and determines the runtime of the combination, right? The way you would generally do this is use that doubling technique to estimate your C, use that C to partition and do your tree packing, right? And with high probability, everything works, right? What if things don't work? How do you know that things haven't worked, and what do you do? Yeah? Exactly, right? If the packing is much, much greater than the cut you found, sorry, much, much less than the cut you found, then you just repeat the whole thing. But this is only going to happen with probability 1 over n4 or something like that, so it doesn't even change the expected runtime significantly. Okay, so this is the high probability runtime and also the expected runtime of this packing algorithm. Okay. All right. Now I can go back to the nice question that you asked. We have this approximately maximum packing. can't we use that to find the exact solution? Right? If I have an approximately maximum packing, what do I need to do in order to get a truly maximum packing? Yes? How many more trees am I going to need to add? Yeah, the whole point of this is that it found a 1 minus epsilon times optimum packing, right? So I need to add epsilon c more trees. How long does that take me? Yeah? Exactly. I have to do epsilon c packings, epsilon c augmentations, and Gabos does each augmentation in linear time, right? So I can first run my approximate packing algorithm and then run my augmentation algorithm to give me an exact algorithm. Right? Okay, what should I do to optimize this? Well, I've got these two terms, right? This gets slower with this gets faster with epsilon, and this gets slower with epsilon growing. So there's a balancing point, right? It turns out that the balancing point is something that if you plug in, you get something like MC to the 2/3 as the runtime of the exact algorithm when you choose the appropriate epsilon. Yeah? But we have a fast way to approximate C. So we use that first, right? But good point. It does still require sampling. Let me point out something else. We now have a faster exact algorithm. What should we do? Yeah, we should. We can turn the crank again, right? We've been in this situation before, where we get this recursion that runs away from itself, okay? And it spirals, just like we saw in the contraction algorithm, that we had this base case where we switched to a different algorithm, but if you keep cranking the recursion, you discover that you never actually need to switch to the different algorithm, okay? So if you go through this iterated process, you end up with a simple divide and conquer algorithm for computing the minimum cut exactly. What you do is randomly partition G's edges in two. Okay, two groups exactly. Pack each recursively. That is, find the maximum packing of trees in each. Okay, combine those two packings, and then augment to a maximum packing. Okay? So, how fast is this algorithm going to be? Well, this is the mystery, right? How many trees are you, right? So we can already start writing down a recurrence, right? We've got a graph with a certain number of edges, a certain number of vertices, and a certain minimum cut, right? And we're basically going to solve two subproblems which have I don't need to write n, it doesn't change, that have half as many edges and half the min cut, roughly speaking, because each of them is a random partition, is a random sample, right? Plus, well, how many trees are we going to need to pack to get from where we are to the maximum, right? If you think about it, what this is really asking is, in these two random graphs that you generated, what's epsilon? And we know the answer to that, right? Because remember, we did all of this analysis with this idea that P equals mu sub epsilon delta over C, right? Or PC equals mu epsilon delta. Yes? Well, in this divide and conquer algorithm, P is a half. Right? Sorry, let me write this as log n over epsilon squared C. Right? But that tells us what epsilon is. It's root log n over C. Okay. So again, we're not picking an epsilon here. But what's happened is, because of our analysis, we can say that if you take half of the edges at random, then cuts will be within 1 plus or minus epsilon of their expectation, where epsilon is determined by this formula. Yes? So we're going to have an epsilon of roughly 1 over root C, which means that each half will pack 1 minus epsilon times C over 2, which is equal to C over 2 minus roughly root C trees. And therefore, you will need to do roughly root C augmentations, which will take you roughly m root C time. And so now we can go back and fill that into our recurrence. M root C. Okay? Any questions? So then the only question is, what happens to, like, how do you solve this recurrence? And I won't crank through the details. I will simply observe that if we ignore the C, right, we have a 2 T of m over 2 plus order m, right, which is like the quicksort recurrence. It would suggest an order m log m kind of thing, right? But in fact, we have a second parameter which is also shrinking geometrically.